Anthony, and just as he said, I'm a PhD student from Cambridge. Before that, I was working at Spotify as a research intern, where I did research on trying to find musical similarities at large scale. But today, I'm going to talk about multimodal sentiment analysis. Right. Sorry. So, many people have worked on sentiment analysis, especially using Twitter data. For example, Park and Powerbeck used emoticons. They extracted tweets and said that every tweet containing a smiling emoticon would be a positive tweet, and a sad emoticon would relate to a negative tweet. Boland et al. Even tried to predict stock markets using tweets. So what you notice here is that we're not using images. And images have become ubiquitous on social media for people to express themselves. And they contain a lot of information. The thing is, it might be very different from standard image classification because it requires a higher level of abstraction to understand what an image means, mainly for two reasons. First one is linked to some implicit knowledge. You need some prior knowledge to be able to understand a meme, for instance. And the second one is the intrinsic human subjectivity that makes every human a human, such that two different people can use the same image, but to express different emotions. So the first thing I had to do was to actually gather a multimodal dataset. And I did that using Tumblr. For those who doesn't know Tumblr, it's a blogging service, and you post things, and most of the time you got some image, some text, and tags. And this is really important because basically we'll be using the tags to collect the label of the post. And it takes a very simple form, such as hashtag angry or hashtag optimistic, hashtag sad, and so forth. By the way, if there is any question, please feel free to just ask me, because if there's something unclear, there's a 90% chance that someone else in the crowd got the same question, so just fire away. So we're using the tags, and this is what we call emotional self-reports, because the person who wrote the post said himself that he was feeling happy or angry when he wrote the post. That's what we want. This is different from the tweets, because these two people use emoticons, but the person who wrote the tweet didn't explicitly say, I was feeling happy, I had happy feelings or negative emotions when I wrote the tweet. So
just a quick question.
Yeah.
So just that I get it right. So you're using the data from Tumblr,
Yes.
basically as labeled data to create your model.
Yes. That's the training data.
And just another question.
Yeah.
Do you account in any way that there might be some irony or something like that in those labels?
Yeah, and actually, I get back to you after, and we can detect this kind of things that occur on social media. Because talking on social media is very different from scientific papers or Wikipedia articles. You can have that kind of things. Second thing that's worth mentioning is that we're trying to have research. I'm not trying to simply predict the polarity, the sentiment polarity, but I'm trying to find the emotional states of social media users. To be more concrete, here's an example of a Tumblr post. You got a big image and then some text. I don't know if you can read back there, but it's written when dogs are back home. And at the end, you got the hashtags. So hashtag social, hashtag home, hashtag happy, and this is what we're looking for. Because of this, we're able to create a training instance with image, text, and a label, which is happy. So the data sets, we've got 15 different emotions. They come from the Palace X scale and the Plutchik's wheel of emotions. And we extracted every Tumblr post containing some emotion tag, starting from 2017. We filtered non-English posts, and we got a total of 250,000 posts. Right. Here's the most interesting part now, maybe. The neural network. How did we manage to use the images and text to predict the emotion? Let's dive in the visual analysis first. If you try to train an image model, you might have realized that it can be quite hard to make it work, and you need lots of data, and you have to try many different architectures before achieving satisfying performances. That's why we took advantage of what we call transfer learning, which is basically taking a model that was trained on a different task, such as on the ImageNet dataset, where you had to classify image according to 1,000 classes, and then retrain this neural network for your own task. And the idea of why this even works is that when you got a convolutional neural network, first layers are going to extract universal simple features such as shapes or arrangement of colors that can be reused for anything image related. And then the top layers near the output layer, they're here to very differentiate each subtleties of the different classes. If I take the ImageNet dataset, there are 1,000 classes, and among these, I think there's about 200 breeds of dogs. And so these late layers, they are here to know what kind of breed it is. And in our case, that's not what we're looking for. Maybe we're just interested in knowing whether there's a dog, regardless of the race. Was that clear? Any question? Cool. Now for the text. We chunk the text into words, and then we use word embedding. The reason being is that if you use something such as one-hot encoding, then you are essentially saying that the distance between dog and cat is the same as the distance between cat and dog, which is not what you want. You want to map your words into a high-dimensional space where semantic relationships are preserved. So when you map dog, cat, and tree, dog and cat will be closer than dog and tree. The second thing is that to understand someone, you got some memory and you know the context. You're aware of what the person said before. So you have to keep track of that, and we're using a recurrent neural network for that. Now, how do we combine these two modalities, visual and textual? Humans, they seamlessly combine different modalities. For instance, when I'm speaking right now, you are hearing what I'm saying, but you're also looking at me, hopefully. And so you can see the movement of my lips and my hands movement as well. That helps you understand the message. And the same thing, I want you to apply the same idea to train neural network, to combine these different rich type of information to predict the emotion. Here is the actual neural network. On the bottom, you've got the input image. So for instance, the two dogs that you've seen. And here is the inception model, 22 layers in total. And we're going to retrain the top layers so that they adapt the abstract features for our task of emotion inferring. Next, we got the input text that we churn into words. And each word, they go through the word embedding. And then there's the recurrent neural network with long short-term memory units. The two modalities are concatenated. They go through a dense layer that hopefully captures the synergy between the two modalities. And finally, you got the output layer. So size 15 because you got 15 different emotions in the dataset. How do you train this neural network? Processing text can be tedious. And if you're using feed-dict to train your neural network, it's hard to use your GPU at full capacity because feed-dict is sequential. So you're essentially making your GPU wait for the data to be prepared. And you'd rather want your data to be prepared in a parallel thread so that it's always ready when you need it. How are we going to achieve that? Well, with the TensorFlow Dataset API, it works the following way. First, you have to convert your data into TF records files, which is simply a file format used by TensorFlow for efficient data storage. So you got your algorithm just explains that you got some image, which is a bunch of pixels, so a matrix of integers, some text that is also a sequence of integers because you can have a one-to-one correspondence between each word and some vocabulary, and a label which is an integer as well. And then after you have converted your data into TF records file, you can create a TensorFlow dataset instance that will consume your TF records files and automatically create a queue so that your data is storage available for your GPU to use. Now the results. We are comparing 3 different models. The image model using only the image, text model using only the text, and the deep sentiment model, which is the multimodal neural network, combining the two. And we compare these 3 to random guessing, which only uses the prior probabilities of the different classes. So on test accuracy, you got 69% with the text model, which is almost double the image model accuracy, meaning that on Tumblr, text is a better predictor of emotion than images, which is not surprising given how absurd and diverse images posted on Tumblr can be. And then the deep sentiment model achieves 80% training accuracy and 72% test accuracy, which significantly outperforms the image model only and slightly outperforms the text model. Now the interpretation of the model. We wanted to know if the model made sense. What were the top 10 words associated with the 15 different emotions you have here? How do you do that? You create artificial posts containing a single word. And you, with this image, you take the mean image per channel mean because you don't want to influence your model with the image. You want to know what's the effects of your single words on the neural network. So you got your artificial post containing one word such as horrible or terrified, goes through the neural network, and then here in the output layer, you got a score for each emotion, and the top 10 here are simply the most excited words for each emotion. The score for happy, loving, enjoy, wonderful was the highest for the emotion happy, and same with the others. And if you take a quick look, looks like nothing is out of place. So far, is there any question?
Actually,
Yeah.
let me ask one.
Yeah.
So if you go back to your evaluation slide,
Yes.
so it seems that when you look at the train accuracy versus text accuracy, I mean, yeah, you'd expect it to be lower, but so especially the drop off for image model and the deep sentiment seems to be quite substantial, which typically is like significant in some form of fitting. So what sort of like validation techniques have you employed to
Good question.
combat that?
We haven't used. So we tried different architectures, but the model can be better if you, as you said, we used validation data to tweak our hyperparameters that just drop out, things like that, to bridge the gap between the train accuracy and test accuracy. This is the first shot, and you can get better. Yes.
What about emojis? Did you deal with those?
No, we're not using emojis. We removed the emojis. Yes.
Yeah, your calm seems to be in the wrong row.
Sorry.
On the next slide, calm is not under calm, it's under pencil.
Calm
You have
is
the emotion calm, but the word calm is appearing at the bottom of the screen.
Oh, I mean here.
Yeah.
Yeah. Because calm is an English word, so it could be treated as such.
I just wondered why it didn't appear against the calm
Oh.
emotion.
You mean? Oh, because we removed the emotion, because obviously it would be the highest scoring words. If high scoring would be happy, calm, sad, scared, and so forth. But so these are the 11th top scoring words. And the second thing I wanted to verify was so this complex model of emotions, saying that emotion can be mapped in a 2D space. And the first axis is called valence, which is basically whether is it a negative or positive emotion. And the second axis is arousal, so how intense emotion is. To do that, we computed the posterior probabilities of a subset of the data that we call y hat, and then we applied PCA on these vectors. So we got prediction on the first and second principal components. The first one neatly separates positive emotion from negative ones. And the second axis, even though so you got this high activation for excited, surprised, and low for pensive, calm, it's not as clear that it is arousal. So it might be evidence against a two-dimension model.
Could you again explain how you arrived at
How I get that?
that?
Yeah. So you take a subset of your data, and they all go through this neural network. So you got, this is the output layer, followed by softmax activation function, which gives the probabilities of each training instance being whatever class. And we do that for a bunch of data, and we got this wild hat. Then you can apply PCA on these 15-dimensional vectors. so that you can predict them in 2D. Yeah. Now, psychologists wonder whether it was possible to have a structure of emotions, or whether emotions being a creation of the human mind, it was too complex to even have that kind of structure. We gave it a try by computing the correlation matrix of the wide-eye paths, converging it into a distance matrix, and doing hierarchical clustering. And the result we have, we got a nice variation of positive emotion, it's actually happy though, from negative ones there, on the right, and some neutral one in the middle, optimistic called pensive. And even within the negative emotions, you got this cluster, anger, shame, and now disgusted, which are emotions that can be used for similar contexts. Same here is all related to surprisingness. So, might be evidence for the structure of emotions, yeah. So, what I've talked about so far is detailed in the paper Multimodal Setting Analysis to explore the structure of emotions, which I'm going to present at KDD 2018. That happens in London this year, so you're very welcome to join. Thank you all for your attention.